So recall the solubility curve graph. What this curve means is given a temperature, it defines the maximum amount of solute that can dissolve in 100 grams of water. So, for example, for sodium at 100 degrees Celsius, so roughly, you can put at most 40 grams of salt in the water to get it dissolved. Any more than this, and it won't dissolve, it'll come out. So, for example, for potassium chloride, you can put 42 grams. Only 42 grams of potassium chloride would dissolve in 100 grams of water at 50 degrees Celsius. We have some terms that relate whether or not it's saturated or not. So we say that if it's on the line, meaning if you put exactly 42 grams into it, it's saturated. It can no longer dissolve anymore. So saturated means that it cannot hold any more solute. No more solute can dissolve. If you were to put, so in that previous example, it stores 42 grams is the most you can put. If you put any less than that, it's called unsaturated, meaning you can still dissolve more solute. We can also have something called supersaturated. It's where we, for some mechanism, we force that remaining solute to dissolve. These are usually very unstable and come out very quickly. So supersaturated is whenever you get more than what can dissolve. And I'll go in a little bit explaining it. So unsaturated solution is when you add less than the maximum solute that can dissolve. I.e., you can still add more and get it to dissolve. Saturated solution is when the maximum amount of solute is dissolved. No more is able to dissolve. And supersaturated is when more than the maximum is dissolved. Keyword is dissolved. So how can you get more than what can dissolve to dissolve? I think I mentioned it last time. Let's go over some examples. Suppose we had a chemical where at most 50 grams can dissolve in 100 grams of water. At the current temperature. So at most 50 grams can dissolve in 100 grams of water. So let's say we have 100 grams of water. If we put 25 grams of solute, it would all dissolve. So this would be unsaturated. We can still put 25 more grams into it. Again, 100 grams of water. If we put 49 grams of solute in, this is still unsaturated. That's because we can still dissolve 1 gram of solute. If we put 50 grams of solute in, this is saturated. Any more would not dissolve. If we tried to put more in, so let's say that we took 60 grams of solute and put it into the water, 50 grams of solute will dissolve, and 10 grams would precipitate, meaning coming out of solution. And this would still be saturated. So just adding more than the maximum does not give you a supersaturated solution. Putting 60 grams into it, we still have 50 grams dissolving, 10 grams would fall out. For it to be a supersaturated solution, so let's put 60 grams of solute. All 60 grams is dissolved. This would be supersaturated. If you tried to do this, you would not get it supersaturated. It would 50 grams would dissolve in, while 10 grams would sink to the bottom. We have a clump of 10 grams at the bottom. So, for example, in this one, 42 grams is the most you could do at 50 degrees. How could you get it super saturated? So if I put 45 grams in, 42 grams would dissolve and 3 grams would go down and it would be saturated. So if I put more than 42 grams, everything over 42 grams would not dissolve. For it to be super saturated, you have to dissolve more. Can y'all think of a way to super saturate it? So if I do it so let's say that I put 50 grams in, and let's say I raise the temperature up to 75. So at 75, if 50 grams can dissolve, it would become saturated. It's not super saturated. What could you do to make it super saturated? You're close. Mm-hmm. You're on the right track. You just need one additional step. Do what? Well, when you heat it up, so let's say you heated it up to 75 and put 50 grams in it, it'd be saturated. So we want it to be oversaturated. So what would you do then? Mm-hmm. What would happen if you then reduce the temperature back down? What would happen to that additional 8 grams that's dissolved in? So, so if we put 50 grams into it at 50 degrees Celsius, 42 grams would dissolve, 8 grams would not. I can force those 8 grams to dissolve by increasing its temperature up to about 75 degrees. So now I have 50 grams dissolved in, but it's at its saturation point. If I were to reduce the temperature back down in a particular way, one of two things will happen. Either that 8 grams is going to fall out of solution or precipitate, or it'll stay dissolved. So, so this is showing salt. We look at here, salt at 0 degrees is about 34. I think they're doing it at room temperature, which is around 20 or 30, which is around 36 degrees. So at most, only 36 grams can dissolve in it. If you put 30 grams, that would be unsaturated because you put 6 more grams. If you put 40 grams in, 36 will dissolve, while 4 grams would settle to the bottom. To make super saturated, they use this example. Glucose, which is sugar. So they say that at 25 degrees Celsius, only 91 grams can dissolve. So at 25 degrees, if they put 100 grams of sugar into this container, only 91 will dissolve and 9 grams will stay as a precipitate out the bottom. So 9 grams wouldn't dissolve, 91 grams would. Now, if you increase the temperature, you change the solubility. You heat it up from 25 degrees to 50 degrees, you can force that last 9 grams to dissolve and even put some more into it. At this point, it's undersaturated. You can still add more sugar. Now, if you very slowly and very carefully lower the temperature, that extra 9 grams won't just come out of solution. At this point, it is super saturated. It's supposed to only contain 91 grams, but because you raise the temperature temporarily to force the rest of it to dissolve, and if you're very careful and do this slow enough, the solution will it won't that extra 9 grams will immediately come out. This is important to understand in chemistry because a lot of reactions are exothermic, meaning they generate heat, and that means more things can dissolve into it. Another thing is when you're doing chemical reactions, you sometimes need to do it at high temperatures to make the reactions speed up, or they don't work under low temperatures. And when you let it cool off, you can end up with a supersaturated solution, and that's unstable. And all of a sudden, your entire solution turns into a solid. Have you ever made rock candy? So this is whenever this happens, we usually do this with crystals. In order for you to form a crystal, a crystal is a repeating pattern. It's I think I showed y'all the super cold water experiment, right? Super cold water. So this is water that is at -10, -20 degrees. Let's look at the H2O molecule. So water molecule looks like this. Whenever it becomes a solid, it has to turn into this nice crystal structure. If it were to bond like this and become a solid like this, it's not that stable. Meaning that these bonds will break and the molecules will be able to slide past each other. That's the definition of a liquid. A liquid is where they have weak connected bonds and they're able to slide past each other. That's how you define a liquid. A liquid is where they're loosely connected together, and if they slide past each other, that's known as a liquid. A solid is when the bonds are strong enough that it keeps it into a definite shape. So for crystals, it has a particular pattern. But the question is how do you get this particular pattern? How does the atoms actually rearrange themselves into this shape? And in order to do that, it actually has to have a starting point. It's kind of a paradox. You have to have ice in order to make ice. Or you have to have a nucleation site. This could be a speck of dust. This could be a cut in the glass container. This could be a pebble. This could be a grain of sand. They could act as a nucleation point and they can grow off that small microscopic speck of sand. But if you have pure water with a smooth inside, you can cool it down to below its freezing point, and because there's no starting crystal to grow off of, it stays liquid. And if you give it a quick shake or tap, you can get a crystal to form, and all these rest of the water molecules start building and attaching themselves to that remaining crystal. Another thing you could do is we have super cold water and some ice here, so we have some starting crystals for it to grow off of. Again, because there's no crystals for the water to start growing at, it doesn't turn into ice. But as soon as you pour it on some crystals, they will start building off of each other. And so the water is attaching and rearranging itself at atomic level onto those crystals and starts building and making more ice. And this is kind of related to super saturated solutions. So he has some sugar, and he put some water in it. He's heating it up. You can notice and see the sugar crystals white. They're not able to dissolve. Still, they're not able to dissolve. Once you get higher and higher temperature, eventually you start clearing up and all the sugar dissolves into the solution. Being careful to pour it into a good container that doesn't have anything. Right now, because it's really hot water, so you're able to dissolve way more sugar into this water because it's really hot. As it cools off, it becomes a supercritical solution. More sugar is dissolved in this than what's supposed to be. But when it cools off, if you do it slow enough, it doesn't all turn into a crystal immediately. If you give it some nucleation point, so a cotton string, and a washer, they will act as seed points where a crystal will begin to form. So this will act as a nucleation point for glucose molecules to attach themselves and start building long chains. So you can see also on the bottom, there's probably scratches on the bottom where it's able to attach, and you start seeing the sugar coming out of solution. That's how you can make rock candy. Now, if you ever made, there's a dish my grandmother likes to make. It's like peanut butter, sugar, and like milk and water. It makes really hard peanut butter candy. Here, peanut butter and other materials act as nucleation sites. So as soon as you start pulling it off, it immediately starts falling off out of becoming so it goes from goes to a syrup, supercritical solution, super saturated solution like syrup, but then immediately hardens very quickly over like an hour or so. Whereas this can go really quickly. So I ordered this, but unfortunately it won't get here for like over a week. I think we'll just after with this lesson whenever it comes in, I will do this. This is very easy to make, or very easy to create a super saturated solution of this, and it's very stable, relatively stable at least. So he's going to drop. So this is sodium acetate, also known as hot ice. It's what they put in those warm packs in your hand. Some of them at least, where if you break it or do something to it, it starts heating back. But he has a single crystal of sodium acetate, so that's going to be your seed, your nucleation site. And he has a super saturated solution of it. As soon as he drops it in, you see the crystals start forming. This is also very exothermic. You might see steam up here as some of the water is boiling. Two 2011. But I plan on doing this next week or whenever it comes in. Yes. So it's coming out of solution. The thing about this one though is, again, we'll learn it later on. It's a hydrate. It means that water physically attaches to the chemical and bonds to it loosely. So it has H2O attached to the chemical afterwards. So this completely falls out of solution and forms a new chemical. And it forms a hydrate. It still has all the properties of the normal chemical. It's just that water physically attaches itself to the chemical. Let's see. All right. He has a small grain of sodium acetate on the table, and he's going to start pouring it onto it. So that'll act as the starting location of crystallization. And the more he adds to it, the molecules will eventually randomly find a good attachment point to the crystal. And the thing about this chemical that's really good is you can make this very, very high. You can see it freezing. This is another PowerPoint. Most of it we've already done was the solution, a homogeneous mixture of two or more substances. And, we have a solvent and a solute. Solute is the part of the solution that's being dissolved, usually the lesser amount. Solvent is usually the greater amount part that actually does the dissolving. So solute is the thing being dissolved. Solvent is the thing doing the dissolving. So to dissolve the solute, when added together, make a solution. So milk and cocoa powder. Solvent is milk. Dissolve chocolate and mix together to make hot chocolate. Soluble versus insoluble. Already covered this. Soluble is a substance that can be dissolved, and insoluble is a substance that can't be. Miscible is a liquid that is soluble in another, and immiscible is a liquid that isn't dissolvable in another. So you can clearly see two liquids on the left. So immiscible. Yeah. Again, we don't really need to know about polarity because we'll learn it later in the year. But nonpolar means that the electrons are shared equally, such as in oil and fats. Polar means the electrons are not shared equally, like in water. So in water, oxygen pulls on the electrons more stronger, and hydrogens become positive, oxygens become negative. And nonpolar, all the atoms pull equally, so that there's no high density of positive versus negative. We'll learn later in the year how to identify and do all this. We'll learn this notation, but for now, just the main thing is just to remember this. Like dissolves like. That means that polar solvents dissolve polar molecules. Nonpolar solvents dissolve nonpolar compounds. Oil is nonpolar, which is why oil and water separate. Which of these sugar cubes will dissolve fastest? See? So we have the same amount of sugar, but breaking it up increases it. What does aqueous mean? What is an aqueous solution? Y'all remember? Aqueous means the solvent is water. So solutions that can conduct electricity are known as electrolytes. Did y'all know that water is one of the best things to insulate electricity? You cannot conduct electricity through pure water. However, if you add ions or salt to it, it becomes an electrolyte and then can conduct electricity. So putting some salt and some pure water will allow it to conduct electricity. However, if you didn't have anything dissolved in water and you had absolutely pure water, it would not conduct any electricity. Any of y'all know what the Z machine is? This is one of my favorite pictures. So this is pure water down here. So this entire machine is pure water. And when you see above the water, it's arcing electricity. So it's all. So in order to prevent all these things, what the Z machine is, in case you didn't know, is the point where we generate the strongest X-rays in the world. We basically take all, like a couple of cities worth of power generation, and cram all of that electricity to a single point in about a nanosecond. So it's a huge amount of electricity all going to a very small point in a fraction of a second. It just produces tremendous X-rays. This is how we simulate the X-rays generated by star collapse and black hole accretion disk. But as you can imagine, trying to dump that amount of electricity into a very small spot, you need to isolate all the components, and they submerge all the components in pure water because pure water can't really conduct electricity. The air conducts electricity way better than the water does. If you're curious about better images, that's the inside of it. That's a submerged. Where is it? The room size area. And people coming into this, that's a target area where they're dumping all the electricity in. So you get crazy high voltages. Sugar wouldn't produce any electrolytes. Acetate is a weak one. Salt is very strong. So ways to increase the rate at which something will dissolve: increase temperature, crush or make smaller, or stir the solution. So unsaturated, a solution in which more solute can dissolve. It will also be below the line. A solution in which it contains the maximum amount of solute. It will be on the line. And this is referring to how much is dissolved. A solution in which contains more than the maximum amount of solute. Dissolved should be a key word in there. Is supersaturated. So supersaturated is a solution that is holding more solute than it should be. It is achieved by heating the solution and then cooling it very slowly. They're also unstable. Dust particles from the air can get in and quickly make it fall out supersaturation. So solubility curves. Solubility indicates the amount of solute that will dissolve in a given amount of solvent at a specific temperature. So if it's on the line, it's saturated. It's above the line, it'd be supersaturated. And this is referring to dissolved. And if it's below the amount, it's unsaturated. So using the available solubility curve, classify as unsaturated, saturated, or supersaturated. So would 80 grams of sodium nitrate be saturated, supersaturated, unsaturated? So looking here, looking there, we see that sodium, so that point is below it, so this is unsaturated. What about the other one, or number 2? 45 grams of potassium chloride at 60 degrees. So it's right there. We're looking at this line. Will be saturated. 30 grams of potassium chlorate. So right here, we're looking at this one. It's above it, so it'll be supersaturated. And the last one. Right here, and then that one will be unsaturated. And this is where I stop.